we were discussing about heat engines, and we also saw Carnot engine in our last class. Today we will discuss more about Carnot engine, see what is the work done by Carnot engine, what is its efficiency, how to calculate its efficiency, and also we will learn about refrigerators, its working. So let me just go through what is meant by Carnot engine quickly. So we saw that Carnot engine is a ideal heat engine, which means it has the maximum possible efficiency, and it consists of a cylinder filled with an ideal gas, and the surrounding part of the cylinder is insulated. It has a conducting base, and there is a frictionless piston. We can move up and down this piston, and there is a source of heat at high temperature T1, and there is an insulating pad and a sink. So let us see what are the cycles, what are the processes through which the system, that is this working substance, which is an ideal gas, go through when a Carnot engine is working. So it goes through four of these processes. The first one is isothermal expansion. Let's see what happens during this process. So this gas cylinder, it is kept on the heat reservoir or the source of heat, which is at high temperature. Now, when it is kept on the source of heat, the base is conducting. So heat energy will be absorbed by this gas, ideal gas, and it expand. So it's an isothermal expansion. So it's a slow expansion where an amount of heat, maybe Q1, is absorbed by this gas. Now, after that, we keep the cylinder containing gas on the insulating pad. Here, see, on the insulating pad. So when it was on the source of heat, it went from A to B, that is from A to B on the graph. Its pressure change, volume change from P1 V1 to P2 V2, but its temperature remained a constant, that is T1, that is the temperature of the source. It has the temperature of the source, and since the temperature is a constant, we call it isothermal expansion. So also remember that when the gas is expanding, work is done by the system. So work is done by the gas. Now when it is kept on the insulating pad, there is no source of heat, so it's an insulating pad, so no heat enters the system, but the gas is still expanding, the gas is doing work. So since there is no exchange of heat, it is an adiabatic expansion. So when it is on the insulating pad, it goes from B to C as shown in the graph. From B to C, it goes through an adiabatic expansion. Again, remember, during adiabatic expansion, the pressure, volume, and temperature can change. Pressure changes from P2 to P3, volume changes from V2 to V3, and temperature changes from T1 to T2. So it undergoes an adiabatic expansion. Remember, again, it's expansion. Work is done by the gas on the surroundings. Now it is kept again on the reservoir, but this time of low temperature, that is the sink. So the cool reservoir, it is kept, it's a conducting surface. So what happens? Whatever extra heat energy here it has. See, it's at very high temperature when we kept it on the source. It expanded. Again, it expanded adiabatically, which means when there is adiabatic expansion, the gas inside cools down. Still, it will have some temperature. So that uh, extra heat energy which it has absorbed is given out into the cool source or to the sink. So here it is undergoing compression. So when it gives out the heat energy, when this air is compressed, what happens? The heat energy must be lost. So when it is compressed, to keep it isothermal at the same temperature, the extra heat energy is given down to the sink. So it's an isothermal compression. During compression, we are pushing the piston down. We are doing work on the gas, and it goes from C to D. So it goes from C here to D. So the pressure goes from P3 to P4. Volume goes from V3 to V4. It's an isothermal compression. So after that, we again keep the gas cylinder on the insulating platform. And again, we are doing work on the gas. We are abruptly pushing the piston down, which means we are further compressing the gas. When there is adiabatic compression, it's adiabatic because it's kept on the insulating platform and there is no exchange of heat. So during adiabatic compression, what happens? The gas will get heated up. See, it goes from D to A, which means its pressure changes, volume changes, volume is decreasing, so it's compression, it's adiabatic compression. Therefore, what happens? The temperature increases. So during adiabatic compression, it goes back to its initial stage A. So these are the four cycles through which the gas will undergo during a Carnot cycle. So this is called a Carnot cycle. And for the heat engine to continue working and continue do work, uh, we have to continue this cycle. So this cycle will go on and on. Is this clear to you what is meant by Carnot cycle? Is it clear the four steps? Is it clear to you?
Yeah, teacher.
Okay. Now let us see what is the work done in a Carnot cycle. So as we saw, in a Carnot cycle, it goes through an isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. So the first two are expansion. So the work done, W1 is the work done as in the first process, process 1 to 2. That is when it is going from state 1 to state 2. So this is isothermal expansion. W2 is the work in 2 to 3, that is adiabatic expansion. So in these two processes, the work done is given by the area under the PV graph. So this is the pressure volume graph. So the work done by the system is W1 plus W2. That is the area under this graph. So this is the shaded region showing the work done as it goes from state 1 to 2 and 2 to 3. Both are expansion. So work is done by the gas. Now, after that, it goes from 3 to 4 and 4 to 1. 3 to 4 and 4 to 1. These two are compressions. So, what is the work done? The work done is represented by W3 and W4 as it goes from 3 to 4 and 4 to 5. So, it is the down part, this area. So, the area under these two curves. Now, when we take the total work done, W1 and W2 are taken positive because work is done by the system. It's expansion. And W3 and W4 are taken negative because here the work is done on the system. It's compression. We are pushing the piston down. So what remains is the area enclosed by the PV curve of the Carnot cycle. So out of this whole area, if we reduce or subtract these area, what we get back is the area enclosed by this cycle. So this shows the work done in a Carnot cycle. Is it clear to you what is the work done in a Carnot cycle?
Yes, teacher.
So it's the area enclosed by the PV curve. Now let us see what is the efficiency of the heat engine and how to calculate it. So we saw that the temperature of the hot source is T1 and the temperature of the sink, that is at low temperature, is T2, and amount of heat energy Q1 is absorbed. A part of it is converted to work and the rest of the energy Q2 is given back to the sink. So the balance is that the rest of the energy, so Q1 minus Q2 is converted to work. So Q1 minus Q2 is equal to W, or the work done. Now, when we calculate efficiency, it's the output divided by the input. So the output is the work done and the input is the energy supplied, that is Q1. So efficiency is equal to W divided by Q1. But we know that W is equal to Q1 minus Q2. So when I substitute, we get Q1 minus Q2 by Q1 is equal to 1, because Q1 is a common denominator, 1 minus Q2 by Q1. And the amount of energy absorbed from the hot source is proportional to the temperature of the hot source. So we can write it as Q1 is proportional to T1 and Q2 is proportional to T2. So Q1 by Q2 is equal to T1 by T2. So substituting instead of Q2 by Q1, T2 by T1, we will get the efficiency as equal to T1 minus T2 by T1. And remember here, if the temperature is given in degrees Celsius, you have to convert it to Kelvin. How can you convert temperature given in degrees Celsius to Kelvin? How to convert?
We add 273.
Yes,
Yeah.
exactly. So, yes, that's right. So, if the temperature of the hot source was 100 degrees Celsius, here in the formula, you have to use 100 plus 273, which is 373. Is that clear to you? So, always when we are using the temperature in this expression, you have to convert it to Kelvin, especially while solving problems. If it is given in Kelvin, no issue, you can directly use that. So the percentage of the efficiency is the whole quantity multiplied by 100. Uh, Usually, a heat engine will have a efficiency between 20 to 25 percent only. The heat engine efficiency is very low. An ideal heat engine having the maximum possible efficiency is a Carnot engine. It is not an actually existing engine because we assume that the gas used, the working substance used is an ideal gas. You know, ideal gas is just a theoretical concept. Real gases have properties different from ideal gas, but in Carnot engine, we consider it as ideal. So Carnot engine has the highest possible efficiency. Still, it can go only up to some 50%. But real heat engines have very less efficiency. It may be only around 25%. Is that clear to you how to calculate the efficiency of a heat engine? Is it
Yeah.
clear? Okay. Now let us see about refrigerator. I hope all of you will have the refrigerator in your home, right? That will be
Yes, teacher.
one of the favorable device or favorite device at home. You have all the food stuff stored in a refrigerator. Why do we need a refrigerator at home? Why do we need a refrigerator at home?
To
So that the
cool.
food.
The food can be saved for a longer time. If you keep food stuff in refrigerator, they will remain at low temperature low temperature compared to the surroundings, and no bacteria will be active when it is at very low temperature, and you can preserve food for a longer time. And your refrigerators also will have one freezer area where you can convert ice into water, and you can also keep meat, fish, other foodstuffs which should be kept at very low temperature, so that it can be preserved for a longer period. Now, naturally, heat cannot flow from a cold body to a hot body. I would like to remind you at this stage the second law of thermodynamics, the Cauchy statement. Cauchy statement, remember, do any one of you remember what is meant by what is Cauchy statement? It states that we cannot flow heat from a cold body to a hot body unaided by an external agency, which means we need an external agency or an external device if we want to flow heat from a cold body to a hot body. That external body is called a heat pump. The Kelvin statement of second law also tells that it's not possible to continuously flow heat from or continuously take heat from a body and reduce its temperature cooler than its surroundings. So in a refrigerator, what we are going to do is we will be reducing its temperature even if it's cooler than its surroundings. A part of that, this area will be cooler than its surroundings. Still, we will be taking the temperature or heat energy from it and giving out to the hot region. So let us see how this device, heat pump, which helps the refrigerator to work, functions. So let's see how a heat pump or a refrigerator works. So this is a diagram representing the working of a heat pump. The blue region is the cold region from where we again take heat, and the red region is the hot region where we again give out heat. So from the cold region, which is blue, we take heat, and the red region, we give out heat. Now, what are the important parts of a heat pump? You have a compressor here, you have a compressor or a motor here, and then you have a gas which is sometimes a liquid, and this gas or liquid is called the refrigerant. Earlier, refrigerant use was freon gas. It's not suitable because it leads to depletion of ozone layer, but nowadays we are not using that. We are using tetrafluoroethane, which doesn't deplete ozone layer. So the refrigerant nowadays we use in the modern refrigerators are tetrafluoroethane, ethane as a refrigerant. Now we are as physicists are more concerned about how it actually works. So as I told, there is a compressor here. Now, once we start the compressor or the motor working, we will start from here. There is an expansion valve where the liquid refrigerant is allowed to expand. When the refrigerant is allowed to expand, when it expands, it cools down, right? So it cools down and the liquid has a lot of space here, so it is allowed to evaporate. So evaporation is a process by which the liquid will take heat from its surroundings and get converted to water vapor. Remember, you can convert liquid to water vapor either by boiling or by evaporation. Boiling will take place at very high temperature, around 100 degrees Celsius, but evaporation can take place at any temperature, even at lower temperature. Remember, we get our clothes dry even in cold weather, even if it takes a longer time. Even in cold weather, we can get our clothes dry. Why? Evaporation can occur even at cold temperature. So here, the refrigerant evaporates, absorbing heat from the surroundings, which is already cold. So the refrigerant will evaporate and the gas is now taken through this coil to the compressor. What is meant by compressor? It compress the gas. So it will compress the gas. When this compressor works and compress the gas gets heated up. So this heated up gas is taken through the coil to this condenser region. So the hot gas will come here and it will release the heat energy to the surroundings, which is already hotter, and it will release the heat energy and it will condense to its liquid state. And this liquid will come here again. If the compressor is working, it will allow, the wall will allow it to expand. So what happens, it cools down and it wants to evaporate again, taking heat from this cooler surroundings. Again the gas is carried here and the heat is released. So this is how a heat pump works, and it works as long as the compressor is on. Is it clear to you how a heat pump works or how a refrigerator works?
Yeah,
Is,
teacher.
I didn't get. Is there any doubt?
No, teacher.
Okay, so let us see, let us just have a quick read of this and we will go to the next slide. The compressor is run by an electric motor, and when the compressor is started, the refrigerant is allowed to expand and evaporate, absorbing heat from the surrounding. That happens here. The pump compresses the refrigerant gas at high pressure and is allowed to pass through the condenser where it releases heat to its surroundings. The liquid again flows through the evaporating coil and the cycle continues as long as the compressor works. So this is the working of the heat pump, or this is the working of the refrigerator. Now a heat pump is not only used in a refrigerator. This is the actual diagram of a real refrigerator. The same idea is used to cool inside a house at very hot weather. So in cold conditions, they also use a heater. So just reverse the thing, then you will get here hot and here cold. That's the same. So the working is similar. Let us see how this works, how in an actual refrigerator works. See, you have the evaporator, or the region through which the refrigerant is allowed to expand is inside the refrigerator, while the condenser, where the vapor is compressed and passed, and where it is condensed to liquid by releasing heat, is kept outside the refrigerator. And here you have the compressor. So once the compressor start working, what happens? At low pressure, this gas goes in and, sorry, here is the expansion wall. So once the compressor start working, the expansion wall will allow the gas refrigerant to expand into this chamber. So it will pass through this chamber, and during that process, it will absorb heat from the refrigerator, and then it will evaporate inside the tube and the gas is carried to this position. And here the low pressure vapor will be compressed to high pressure and they are allowed to condense or turn back to liquid by releasing heat. Again, this warm liquid is allowed to cool down by absorbing heat from the refrigerator by the expansion valve, and this go on. So similar is this working. So that's how a refrigerator and a air cooler works. Is it clear to you? Is it clear to you?
Yes, teacher.
Okay. So let us see more about that. The efficiency of a refrigerator. We usually don't call it efficiency. Usually we use the term coefficient of performance when it comes to refrigerator. We usually use the term efficiency for a heat engine and coefficient of performance for a refrigerator. Now, a refrigerator performs Carnot cycle in reverse order. See, in a heat engine, it goes from A to B, B to C, C to D, and D to A. But in a refrigerator, it's the reverse. See, A to D. It's adiabatic expansion. Adiabatic expansion of gas, then isothermal expansion of gas, then adiabatic compression. You remember the steeper curve is adiabatic, less steeper curve is isothermal. So this is adiabatic compression, isothermal compression. So it goes in the reverse way. The same Carnot cycle run in the reverse direction. That's how a refrigerator works. And also when we look into a diagram similar to that of a heat engine, see, the heat energy is taken from the cooler region. That is from the inside of a refrigerator. The heat energy is again taken and we do work on the system, on the refrigerant from outside, and the total heat energy is given to the hotter outside air. So here, from the cool region, heat energy is taken and along with some of the work done, it's totally given to the hotter region. This is how a refrigerator works. And uh, that's what we explain now. Absorb heat from the cold reservoir. That is the amount of heat absorbed, QC, will be bigger than zero. Some amount of heat is absorbed. And the work is done on the engine, or the work is done on the system. So the work done should be negative. That's why it's written work done is less than zero, which means the work done is negative. Now the heat is dumped into the hot reservoir, which is outside, which is hotter than inside the refrigerator. So the amount of heat given out is also greater than zero. For energy balance, we can tell that the magnitude of the work done will be the difference in the energy given here and the energy taken. So the magnitude of the work done is equal to the magnitude of the heat energy given minus the magnitude of the heat taken. And the coefficient of performance. We like the refrigerator to perform by doing less work, right? We don't want the refrigerator to use more electrical energy, more work by the compressor. So we prefer a refrigerator which use less work and take away more heat from inside. So we say that the coefficient of performance is good if with less work done, with less electrical energy, it takes more heat from the inside of the refrigerator. So the coefficient of performance represented by K is equal to QC, that is heat taken from the refrigerator divided by work done. And also we know that work done is equal to QH minus QC. So when we substitute that, and we know that the amount of heat taken depends upon the temperature itself. So TC divided by TH minus TC. TC is the temperature, cooler temperature, that is temperature inside the refrigerator, and TH is a hotter temperature, that is the temperature outside. So Tc divided by Th minus Tc. Now, what is the unit of temperature here? Can you tell me what is the unit of temperature here? What should be the unit of temperature there? Should it be in degrees Celsius or Kelvin?
Kelvin.
It should be in Kelvin. So here again, when you are calculating the coefficient of performance, you have to remember that the temperature, if it is given in degrees Celsius, you have to convert it to Kelvin. Now, can you tell me what will be the unit of the coefficient of performance?
Kelvin, right?
Kelvin in the numerator, Kelvin in the denominator.
There won't be any unit.
Yes, there won't be any unit. Similarly, efficiency as such doesn't have any unit, but if we are presenting that in a percentage, you just have to multiply that fraction with 100 and you can express. Also, coefficient of performance, you want to represent that in percentage, you can just multiply this fraction with 100 and represent. But as such, it doesn't have any unit. Is it clear to you? The efficiency of a refrigerator and the coefficient of performance? Is it clear?
Yes, it's clear.